Welcome to clickmyproject.com. Let's discuss about the product. Our product is FPGA based partial reconfigurable FIR filter design. This paper proposes a partial reconfigurable FIR filter design using a systolic distributed arithmetic, that is DA architecture, optimized for FPGAs. To implement computationally efficient, low-power, high-speed, finite impulse response filter, that is FIR filter, a two-dimensional fully pipelined structure is used. To reduce the partial reconfigurable time, a new architecture for the lookup table, that is LUT, in distributed arithmetic is proposed. The FIR filter is dynamically reconfigured to realize low-pass and high-pass filter characteristics by changing the filter coefficients in the partial reconfiguration module. The design is implemented using XUP vertex. That means the design can be executed in XUP vertex. Finite impulse response filters, most fundamental components in digital signal processing, are generally implemented on dedicated hardware rather than software for high-speed computation. Because of the requirement of low-power, high-speed implementation of FIR filter design, in various embedded applications, it is necessary to design reconfigurable filter architectures based on power or resources consideration, or simply to implement new functionality on the run. FPGA is one such platform which allows adapting hardware resources to meet time-varying requirements in power, resources, or performance, and at the same time maintaining a good speed of operation. In the literature, several efficient hardware architectures are developed using non-reconfigurable or reconfigurable architectures. One of the challenges in partial reconfigurable architectures is the reconfigurable overhead, which is the time spent for reconfiguration on the fly. Because of the computational complexity and the reconfiguration time of the FIR filter increases with the increase in the filter order and the type of arithmetic used. As multipliers consume more power in multiply and accumulator, that is MAC operations, several multipliers less schemes have been proposed in the literature. Distributed arithmetic methods is one of the multiplier less technique which uses memories. A reconfigurable FIR filters has been proposed earlier using Xilinx reconfiguration tool. That means they have used the FPGA, vertex FPGA tool as a hardware part. In this paper, a systolic based DA architectures with a dynamic reconfigurable module to reconfigure the filter coefficients is proposed. Let's see the flow diagram of our design. So this flow diagram states what is the process included in our process. Initially, input bit samples are taken, that is, inputs are given as a bits that may be zeros or ones, and then the delay circuit is obtained the input, and the delay circuit is connected with a partial protect generator flag, and then the error bit samples are delayed unit, and the delayed unit processed to the same partial protect generator flag, and the output from the generator flag goes to shifter tree flag. So there the tree adds and delayed and the add unit. Final outputs are obtained as a bits. Let's discuss about the product. This is a demonstration of our product. So as we already discussed, our product development is based on Xilinx. That means our product language is VHDL. That means very hybrid description language. So for this VHDL programming language, we are using Xilinx ISE version. So this is the Xilinx ISE simulator used for our product. So this is the current directory. These are the files included in our process. So all these files, the submodules files included in our process. So these all files are representing decoder and main RTL simulations. So up to the process which we are developed will be placed here. So half adder XOR gates. So usually in VHDL every programmings are based on the XOR logic gates functions. So here by using logic gate functions we have designed shifting and tree process and main RTL and similar process. So this is the main module. So you can see this is this shows us this is the main module. So this is the synthesis report block. Here you can see the modules, what are the files here. Console, this is shows the process, running process, during the running, what are the things happening here. So for example, if your running is running completed successfully, like that, it will show. This will show the errors during the program, and this will show the warnings. So see, I have selected the main module. So for to run the process, we have to select the main module, and I am implementing the design. So that means initially I have selected this implementation. So by selecting the implementation only, I can process the implement design. So and then we have to go for synthesis. So our result source console, here we have completed successfully, process translate completed successfully. So for every step-by-step process, the console will show what are the things happening during the backend and during the simulation. So this shows the continuing running process is continuing, and so these all are the submodules. The main module will recall every process. The submodules are called and recalled from main module. So here this block is the main module of our process. So during the running time, the CPU result and performance also will be displayed in console. So you can see the CPU computation time. So the mapping process, everything will be visible in console. So step-by-step process are processing here. So all over the process, because we have included a lot of submodule functions, so it will take some time to process. So here I am going to check RTL simulation. I am seeing RTL. This is the main block of our product. So while double clicking, you can see the inner blocks included in our product. So you can see what are the files, overall blocks included in our process. So each individual block also consisted of interconnections. So the interconnections, all the interconnections also will be visible. So you can see each interconnection by double clicking it. So similarly we have designed our product. So this is the RTL simulation. And for the simulation of the product, you have to select the simulation, and by selecting this main module, click simulate behavior model. This will open our iSimulator. So during that simulator, we can give input parameters, and by checking the timeline, we can verify the process. So this is the timeline. So we have to apply the input. For the corresponding input, we can obtain the corresponding output. Thank you.